posting up the soccer tips right after class? So we,
I mind a little bit, but I will.
okay. All right.
Yes, always ask. If you want something, if you want a resource, do ask. So yes, absolutely. That way you don't have to wait until right before the exam for me to post all of the quizzes. All right, so quick review from last class, and then we move into some practice. When genes are unlinked, separate chromosomes, they independently assort. We just saw that. That was part of the Socratic quiz. When genes are on two separate chromosomes, when A's and B's were on separate chromosomes, we expected that 1-to-1 to 1-to-1 ratio. There were two parental type gametes, two recombinant gametes. That's independent assortment. That equal ratio of parental and recombinant types. Big A's with little b's, big A's with big B's, and so on. That's what that middle paragraph says. If there are approximately equal types of parental and recombinant haplotypes or gametes, that's the information we need to know that two genes are unlinked. When independent assortment is occurring, we get equal numbers of parental types and recombinant types. So, fill in the blank. If there are significantly more of which type of haplotype, then you have evidence of linkage. So if you have more parental types than you expect, that means recombination is not happening between the two genes you're looking at. That means they're linked. It has to be heterozygous. If they're homozygous, you can't detect. That's a great point. Good insight. Genes, if you've got homozygous genotypes, then you never see recombination. That's why we use dihybrids a lot. Right. So it's when there are significantly more parental haplotypes than you expect. That's evidence of linkage. Less recombination than you expect if the genes were on separate chromosomes. And that's why the default assumption is the law that we all know generally to be true. So when genes are unlinked, independent assortment occurs, and you get equal numbers of recombinant and parental haplotypes. If there's any difference from that, then there's evidence for linkage. And note this word here, significantly. Hence, chi-square test. So we want to know, is there just a little difference in expected versus observed recombination, or is it significantly more or significantly less recombination? And that's why we're talking about chi-square test. So I wanted to make this really explicit. Not in the swearing sort of sense. This is full frontal meiosis. That's bad science humor. So in this case, I wanted to show you exactly what's happening in multiple cells during meiosis at once. So we've got 8 different cells here. All of them just completed synthesis. They're about to go through, each of these 8 cells is about to go through meiosis and produce how many gametes per cell? 4. So we're going to wind up getting how many gametes out of all 8 of these cells? There should be 32. So there should be 32 gametes produced and then 32 haplotypes produced from those 8 cells. So what are those haplotypes? What are the different combinations of A's and B's that we're going to make? Big A, so different chromosomes assort independently. So we're going to get big A's with big B's, like there. And then what happens at the same time when that cell in the upper left is going through meiosis? We're going to make 2 gametes that have the big A with the big B. And 2 that have little a and little b. So far we've tallied 2 big A, big B's, 2 little a, little b's. This is, by the way, scenario 1 is when what are these genes? Linked or unlinked? So scenario 1, genes are unlinked. So the important thing is we're going to see what the number of recombinant types is and what the number of parental type haplotypes is. That's what we want to figure out. That's genetic distance. We're going to figure that out down in the bottom left here. So what about the other 7 cells? How many more big A, big B's do we get? There's 2 there, 2 there, and 2 there. So that's a total of 8 of the 32. All these ones I've circled in black. So 8 of those 32 gametes are going to be big A, big B combinations. This is all Punnett square. It's just a different format. So what happens if we look at little a's with little b's? How many of those are there? Should be 8. We've got 2 there, 2 there, 2 there, and 2 there. This is because the chromosomes are aligning in random orientations, as we've discussed. And then each pair of chromosomes, a chromosome 2 and a chromosome 1, each going into a gamete after meiosis, we should get a 1-to-1 to 1-to-1 ratio. So likewise, we're going to see big A's with little b's and little a's with big B's, also 8 of those. So that totals 32 gametes, which is what we expected to see. Punchline, take-home message. What's the genetic distance between genes A and B? Or let me take a step back. What's their physical distance? Infinite. It's undefinable. There is no physical distance between these 2 genes. They're on separate chromosomes. So it's only meaningful to talk about physical distance between 2 genes if they're on the same chromosome. That's the only time we can say there are a certain number of base pairs of DNA between them. But what's the genetic distance between A and B? How do we calculate that? What's the formula? Number of recombinants divided by the total number of gametes. Total. So recombinant gametes or recombinant haplotypes divided by the total number we observed. So now all you have to figure out is which of those 4 haplotypes are recombinant and which are not. That's the numerator, number of recombinants. How do we figure that out? How do we know which haplotypes are parental and which are not? It's the part up here that we haven't filled in yet, the P0 gamete haplotypes. That's why we always use homozygous P0 parents, because we know their genotypes. So what are the haplotypes that a big A over big B, A, little b over little b parent produces? Big A, little b. And the opposite is true for the other P0 parent. So you know that all of their gametes, parent on the left, all of their gametes are going to be big A with little b, because they're homozygous for both. And the opposite, the reciprocal, I guess, is true for the parent on the right. So now we know that those 2 that I'm circling there are the parental type gametes, which means that big A with big B and little a with little b are the types that weren't present in the P0 generation. Those are our recombinants. Big A with big B and little a with little b. There are 16 of those total, 8 plus 8, divided by the total of 32 gametes we looked at. And the genetic distance is 0.5. What's the unit?
Recombinance fraction?
Yeah, that's recombination fraction, because look, it was a fraction, 16 over 32. So if we want to make that centimorgans or map units, that would be 50. If you remember anything at all from this, especially since it's Friday and everybody's looking excited, what's the distance you expect, or the distance you observe, when genes are unlinked? We just calculated it. Every time, yeah, half, 0.5, 50 centimorgans. Every time genes are on separate chromosomes, they should obey Mendel's second law, independent assortment. Big A's with big B's and big A's with little b's are equally frequent. There's a 1 to 1 to 1 to 1 ratio among the two different recombinant types and the two different parental types. So the number of recombinants equals the number of parental types. You get 50% recombinants, genetic distance of 50 centimorgans. That's the largest genetic distance you should ever calculate. That's one extreme. Genes are unlinked, 50 centimorgans apart. Yeah, please.
So 50 centimorgans is the largest we should ever create.
Yes. In theory, 50 centimorgans is the largest genetic distance you would ever see. We're going to see in the next case, the next scenario, why that is. 50 is kind of a weird number. Like, what, can't it be 100? So we're going to see now why it can't 100. Scenario 2, loose linkage, which again, as I said in the video, is not really a scientific term. So I'm going to put loose in quotation marks. So now we've got genes on the same chromosome. This is another extreme case. I'm just trying to give you the periphery of what's going on here. We've got the case where genes are on separate chromosomes. We've got this case where genes are as far apart together on the same chromosome. What do you think the third scenario is going to be? Don't look. When the genes are on the same chromosome and right next to each other. So there are three extreme cases that we're talking about today to learn how to calculate genetic distance. So loose linkage. Okay. What I want everybody to do is pick one of those 8 cells. I'm going to do the first one. Pick a spot where crossing over is going to happen. I just randomly picked the middle of the chromosome. Pick 2 of those we've done this before. Pick 2 of those chromatids to undergo a recombination or a crossing over event. So pick one on your screen, do just what I did. Pick a spot along the chromosome from top to bottom, draw a crossing over event between any 2 of the chromatids, doesn't matter which 2. So somebody who's done this, I'm going to fill in this second cell here, which we're going to assume, let's define, we're just going to call these briefly 1, 2, 3, and 4 from left to right, just so you can tell me what you did. Okay. So which 2 chromatids did you cross over, sir?
2 and 3.
2 and 3. Okay. And I'm assuming it was between A and B because by definition, crossing over has to happen between these 2 genes. Has to, because they're at the opposite ends of the chromosome. So I don't need to ask you where you drew the crossover event. All I need to know is which chromatids did you pick. Somebody else? 1 and 4. Okay. 2 and 4, I heard. What was that? 3 and 4. So we're just doing random recombination. This is how recombination works during meiosis. Different cells, different spots on the chromosome, different chromatids are involved. Someone else. I need 3 more volunteers to be brave enough to say 2 numbers between 1 and 4. 1 and 3.
Maybe 1 and 4?
1 and 4.
1 and 2.
And 1 and 2. Thanks. Okay. Now, this doesn't work exactly, this is good. This doesn't work exactly as you hope, but it's close. So what's the genetic distance? This is an illustration of how scientists get the information they need to calculate genetic distance. Because what is the unit of genetic distance? Centimorgans, map units. What's it about? What's it measuring? It's measuring frequency of recombination events or crossing over events. So we need some way to observe, not with our eyes though, we need some way to observe where crossing over events are happening and which chromatids they're happening on. We do that not at this stage. This is what happens during meiosis. We do it afterwards, after the gametes are produced and fertilization happens. So we'll just do a couple of these for evidence. So my crossover, how many recombinant types are produced up here in panel 1? So we've got big A with, big B. So that's recombinant type, because there were no big A's and big B's in existence already. And at the same time, we get a little a with a little b. But here, again, I know it takes me a long time to get to the punchlines. This is the good part. One crossover event per meiosis per tetrad. We all agreed on, because I told you to agree on it about a week ago. That was one of our assumptions in meiosis. One crossover event will happen in every tetrad in every cell. What happened to the other two chromatids up there? What happened to them? Nothing. So those two are what sort of haplotypes? Parental. What fraction of those four are parental types? Half, 0.5. So every meiosis, half of the chromatids don't get touched by crossing over, so you always get 2 of the 4 chromatids being parental types. Genetic distance of 50 is the maximum, because the other 2 chromatids are going to be involved in a crossing over event. They might produce recombinants. So in this case, now, this is interesting. I invite you over the weekend, if you're interested, to figure out, using these data, because I'll do this on either a midterm or on a final, most likely, I'll give you this sort of a figure with the crossing over events drawn on. I'm going to ask you, what is the genetic distance drawn here? So over the weekend, if you want, see if you can figure out how to do that just with this visual information. This is not normally the information scientists use. This is a description, a depiction of this information scientists use to calculate crossing over, but this is not normally what it looks like when it comes to us. I'm going to show you that in just a second. The punchline here is that when genes are at the opposite ends of the chromosome, right? This is the thing to write down if you have been tuning out. Genes are at the opposite ends of the chromosome. What's the genetic distance between them? 50%. It's 50%, because there is always going to be a crossover event between 2 of the 4 chromatids. Those are your recombinants. And 2 of the 4 will always be parental. So, linked genes, but at the opposite ends of the chromosome, also 50 centimorgans apart. So, one extreme, genes are unlinked, 50 centimorgans apart. Second extreme case study, this one, genes are on the same chromosome, they're linked, but they're still 50 centimorgans apart.
Is there some kind of connection to unlinked genes with this? Because the recombination event would be something that would have happened if they were on separate genes.
So there's no connection, get it? Unlinked genes, but that's the same idea, is that both independent assortment when genes are on separate chromosomes and this, they're both called recombination. Recombination of genes that are on separate chromosomes is called just recombination. That's independent assortment. This is called meiotic recombination, when crossing over recombines alleles. The one we looked at before, recombination, just had to do with how the chromosomes lined up during meiosis. So there's two different types of recombination. I'm not going to test you on that. So, I think we've already talked about this, so I'm going to let you do this by yourself if you want. It's exactly the same exercise. You pick 2 chromatids, you draw a crossover event on all 8, and my hope is that you never happen to randomly pick a recombination event that happens between A and B. Or maybe you do by chance. Maybe one of these has a recombination event that happens between them. So what's the genetic distance between these genes going to be? Scenario 3 is tight linkage, where genes are very close together on the same chromosome. This was part of the Socrative quiz. Right? Genetic distance is going to be close to 50, close to, it's going to be small. Because we measure genetic distance by recombination events, and if recombination rarely happens between these 2 genes, then the genetic distance is going to be small. Probably approximately 0. If 2 genes are so close together on the chromosome that recombination never, even by chance, happens between them, then by definition their genetic distance would be 0. So that is the range of genetic distances we can calculate. So now you can fill in this table if you want. If you're going to memorize anything from class today, this is probably the thing to memorize. What are the maximum and minimum genetic distances you could calculate when genes are linked and when they're unlinked? I'm going to let you fill that in. If you've got questions about that on Monday, then we can talk about it then. So when genes are unlinked, separate chromosomes, what's our expectation for their genetic distance? Getting back into chi-squared analysis now. We're going to try to tie that piece of this story up. Why we use chi-square analysis when we talk about linkage. Genes are on separate chromosomes. They should be 50 centimorgans apart. So then fill in the other 2 blanks. One of them is going to be recombinant, one of them is going to be parental. When genes are linked, there will be more recombinant types, more parental types than recombinant. Significantly more. So we know we have an expectation and we have observation. We expect to see equal numbers depending on the cross, but with the crosses we're going to use in class, like dihybrid test crosses, we're going to expect to see an equal number of parental and recombinant haplotypes. If there is a significant difference between that expectation and what we see, then that tells us that genes are linked. So the question we want to know about Mendel's genes are, were those genes that control pollen shape and flower color, P and L, linked or not? Give me some input. Thank you. Yes is not input. Well, it's an answer to a question that I didn't ask yet. Okay, here's the question. Did you, when I invited you to calculate the expected number of these different F2 phenotypes, did you? Oh, I'm glad to hear you did. You said yes. So what are those expected numbers from that Google sheet? So 240.2? 80? Is that what I heard? These should be the same, those 2. And then What? 26 point,
The 80s were 80.06.
yeah. This is exactly why this is sometimes problematic. So here's my version of that Google Sheet, just so I can double check, but looks like we're in agreement. So with rounding, it's like 240, 80, 80, and 26.7 or something like that. How did we get those numbers? I know I've talked to a few of you about that, but this is really critical.
Yeah, on this slide.
So if we have 427 individuals, I just want to make sure we're all on the same page doing this calculation. 427 individuals, how do we calculate 240.2?
With the ratio over,
So the total of the ratio is 16. So we expect 9/16 of the individuals that we observe to have purple flowers and long pollen, that top genotype. So that 240.2 is 9/16 of the total number of individuals. So that was 427 times 9/16. Right. That 9:3 to 3:1 ratio came out of the dihybrid Punnett square. So all we're doing is converting that from fractions into actual expected numbers of individuals that we would expect to see. So the sum of those expected numbers will also be 427 if you don't round. So that's a 9:3 to 3:1 ratio of individuals, 240 to 80 to 80 to 27. Now, the question the geneticist wants to know, remember, we're talking about linkage. Are those expected numbers, just answer it simply, first thing that pops into your mind besides go away. Are those numbers, the observed and the expected numbers when you look across, are they the same or are they different? They're different, right? Plain and simple. They're not the exact same numbers. How different are they? Are they significantly different? What information did we calculate on that spreadsheet that tells us if they're significantly different? So we got a chi-square value, and then we converted that into a p-value. What was the p-value for those of you that calculated it? 0. Check it out. This is just because statistics is not entirely accurately calculable with a spreadsheet, but I wanted to make sure that that wasn't just rounding. When I saw I did the calculation, it said 0. It can't really be 0, can it? So I looked, and I looked, and I looked, and I made more decimal places. It's 0.0 forever, right? Basically, the p-value is 0. It's tiny. It's minuscule. You're yearning, I know, from your feedback, the last Socrative exit quiz, to know what the hell a p-value of 0 means. So a lot of you said, yes, I know how to calculate a p-value, but interpreting it is something that I still don't get. That's totally normal. Me too. So what does it mean that there's a p-value of 0? The probability of something is 0. So it's most, I heard two different answers. They're both right. The one I heard first was the probability of the null hypothesis. That was our expectation. What were we expecting? What did we use to calculate these expected values? They're unlinked. Mendel's second law, interdependent assortment, genes are on separate chromosomes. That's what we expect. P of 0 means that expectation, there's a probability of 0 that expectation is correct. So when you have a p less than 0.05, that means a 5% or less chance that your null hypothesis is correct. So if there's a 0% chance these genes are unlinked, then they're linked. There you go. So we have statistical evidence that these genes, P and L, are on the same chromosome. That's it.
So if you have something that's 0.5 or lower, you are 95% or
Better. Yeah.
chance that it is the null.
If you have a p-value of 0.05 or less, there's a 5% or less chance that your expectation is correct. That genes are unlinked.
Saying 95% the other.
Or 95% or greater chance that they are linked. So 0.05 means there's a 55% chance the null hypothesis is correct or supported. 95% chance that your guess, your expectation is wrong. Genes are not on the same chromosome. I really want to impress upon everybody because this is critical, and I got more feedback from you the last Socratic exercise when I asked why are we doing this in class, and some of you said because it's hard, and because we need practice doing it because it's going to be on an exam. Yeah, you're right. But others of you went a little bit deeper and said, well, this is important to know for analyzing data, for making good decisions as adults in this society, and so on. So, I just want to remind, or tell you, if you haven't heard this before, 0.05, I said last class, it's kind of arbitrary, right? 5% chance. Like, I wouldn't bet my life on like 5% chance. Scientists just sort of arbitrarily chose, 5% chance of being wrong. We could live with that. So they said that 0.05, just arbitrarily, 0.05 is a random number. To say that's going to be the exact number where something's either linked or not. Right? What if it's 0.051? Is that really importantly different than 0.049?
Depends on when you're testing it, so.
Yeah, so it depends on the circumstances. So all I'm trying to impress upon you is that 0.05 is an arbitrary number. So although I'm being very explicit about saying it's kind of making it seem like it's black and white, that if it's 0.05 or less, then the genes are linked, null hypothesis is rejected, or if it's greater than 0.05, they're not. Right? That's how we in this class are going to interpret statistics, but in reality, if there's a 5% chance you're right, 1 out of 20 times, you're going to conclude that the genes are linked and they're really not. So it's just an arbitrary number.
That's why you kind of take the safety measure that I'm saying, like, reject the null rather than
That's-
saying it's not true.
That's why you say you reject the null hypothesis instead of accepting your other hypothesis. Safer. Exactly right. So, let's see. We covered the Google Classroom exercise. What was that? So, quick summary, and then I'm going to leave you with a few questions to work on for next class, because there's no reading, no new movie for next class. We're just still doing practice of calculating linkage. So, when you have equal numbers of recombinant and parental gamete haplotypes, your genetic distance is going to be equal number. You have 27 parental types and 27 recombinant types. You take the number of recombinants, 27, you divide that by the total number, which is twice 27. Right. So what I want you to do is to look at this summary, look back through the notes, reconvince yourself of how these calculations work. When there are more parental haplotypes than you expect, then genes, you have evidence of genes being linked. Fewer recombinants than you expect. And that gives you a distance between genes of between 0 and 50 centimorgans when they're linked. We're going to see next time we get together how geneticists did this before they knew about DNA. Because all of the data I've actually shown you, the P and the L, purple flowers, red flowers, pollen shape, Bateson, Punnett, Mendel, none of them, DNA didn't even, well, it existed. The idea of DNA didn't exist. Right? Nobody knew about DNA until the early 1900s. So how did they figure this all out when they didn't even know anything about genes, alleles, haplotypes, or DNA? All they had to work with were phenotypes. All they could do is see the plants, and somehow just looking at the plants and their colors and pollen shapes, figured this all out. So we're going to look at that next class. So these last few slides are just some sample questions that you should work on if you want to be prepared to have an engaged discussion for next class. Have fabulous weekends. I'll see you on Monday.